A tanker sits on the apron of an airport. Not near the airport, on it. The vessel is a laden crude carrier, 330 meters of steel from bow to stern, and according to the position it is broadcasting to every receiver within radio range, it is parked between two runways in southern Iran, several miles inland, holding a steady speed of 11 knots across dry ground. It is not there. It cannot be there. Nothing that size has ever been there. The ship is at sea, somewhere in the approaches to the Strait of Hormuz, doing what it was doing an hour ago, which is making its way toward a choke point that carries a fifth of the world's traded oil. The crew is fine, the engine is fine, the hull is fine, the satellite navigation receiver on the mast is fine too, in the narrow and unhelpful sense that it is doing precisely what it was engineered to do. Listen for signals from space, measure how long they took to arrive, and solve for a position. It listened, it measured, it solved, and the answer it produced is a place where a ship cannot float. The maritime intelligence firm Windward, which tracks vessel movements for insurers, port operators, and governments, reported that in a single 24-hour window in early March of 2026, more than 1,100 vessels in the Middle East Gulf had their positions corrupted this way. Ships appeared on airports, ships appeared in the desert. At least one appeared to be transiting a nuclear power plant. The tracks they drew on the screens of the people watching them were not the tracks their hulls were cutting through the water. And for a while, nobody watching had a reliable way of telling which was which. Here's what makes that more than a curiosity. This is not a story about a broken gadget. Nothing broke. Every component in that chain performed to specification. The satellites transmitted. The antenna received. The receiver computed. The bridge display drew. The automatic identification system took the number it was handed and pushed it out over very high-frequency radio to every other ship in the area, in perfectly good faith, because that is its job, and it has no way of doubting the input. A chain of working parts produced a lie, and it produced that lie confidently, without a single alarm, in a stretch of water that offers less room for a mistake than almost any other commercial seaway on Earth. So the question is not whether something failed. The question is why this particular place, out of every crowded seaway on Earth, has become the one where a technology the entire modern world quietly leans on stops being trustworthy. And the answer turns out to be a machine. Not a metaphorical machine, a real one, with 4 moving parts that only produce this outcome when all 4 are engaged at once. The first part is the shape of the water itself. Hormuz is narrow in a way that most people who use the phrase narrow strait do not really picture, and the lanes that ships are actually permitted to use are narrower still by a factor that will probably surprise you. The second part is the sheer weight of traffic that has to fit through that opening, and the physical characteristics of the individual ships doing the fitting, their draft, their turning circle, their stopping distance, the amount of ocean a loaded very large crude carrier needs before it can meaningfully change its mind. The third part is the radio environment above and around the strait, which over the past several years, and dramatically since late February of 2026, has become about as electronically contested as any civilian seaway gets. And the fourth part is the one almost nobody outside the field knows about, and it is the one that makes the other 3 matter. The satellite signal that every modern ship depends on to know where it is arrives at the antenna weaker than the background noise the receiver is already generating on its own, not weaker than nearby radio stations, weaker than the electrical hiss produced by the receiver's own components sitting in a room at ordinary temperature. That is the design working exactly as intended. And once you understand why it was designed that way and what that design costs, everything else in this story stops being mysterious and starts being obvious. The aim here is that you should end up able to explain the whole failure yourself to somebody who has never heard of it, without needing to remember a single number. That's why it's worth laying out in this order. The Strait is a system. Systems can be understood. Let me be careful about something at the outset, because this subject attracts a lot of loose talk, and the loose talk does real damage. There are at least 4 completely different things that can put a wrong position on a ship's chart display, and they get blended together constantly in coverage of this region. The first is jamming, where a transmitter simply floods the frequency band with power, and the receiver loses the ability to hear the satellites at all. The second is spoofing, where a transmitter broadcasts counterfeit signals that imitate the real ones, and the receiver locks onto the fakes and computes a false answer while believing it has a good one. Those two are related, but they are not the same, and crucially, they feel completely different on the bridge. The third is ordinary equipment fault, a corroded antenna connector, a firmware bug, a chart data mismatch, a setting somebody changed 3 watches ago and nobody wrote down. The fourth is human error, which has been putting ships in the wrong place since long before satellites existed and has not stopped doing so. Every serious investigator working in this space spends most of their effort separating those 4, because from the outside, at a distance, through the filter of a tracking website, they can look identical. A ship in an unexpected position is just a ship in an unexpected position. Whether it got there because somebody attacked its receiver, or because its receiver had a bad day, or because the second mate misread a bearing, is a question that usually takes an investigation to answer and sometimes never gets answered at all. I'm going to hold that line the whole way through, where an authority, a flag state, a class society, a company, or a formal inquiry has reached a conclusion, I'll say who reached it. Where the cause is contested, I'll say it's contested. And where nobody has been able to establish who was transmitting what from where, which is more often than you might expect, I'll say that too, because unattributed is a real and honest category, and pretending otherwise is how a navigation story turns into something worse. That said, the phenomenon itself is not in doubt. It is measured, logged, reported through formal channels, and published in advisories that professional mariners read before they sail. The United States Coast Guard runs a system for filing satellite navigation problem reports. The United Kingdom Maritime Trade Operations Organization collects and publishes incident reporting from the region. The Joint Maritime Information Center issues advisory notes with counts of disruption events. In one advisory note issued in the second week of March of 2026, the center recorded more than 600 satellite navigation disruption events across its operational area in the preceding 24 hours, with documented effects including positional offsets, automatic identification system anomalies, and intermittent signal degradation. 600 events in one day, in one region. That's not an anomaly. That is a condition. And conditions have causes. So let's build the machine, one part at a time, starting with the water. Pull back far enough and the Persian Gulf looks like a mistake in the coastline. It's a shallow inland sea, roughly 600 miles long, with only one way out. At the eastern end, the land closes in from both sides, Iran coming down from the north, and from the south, a spur of rock called the Musandam Peninsula, which is not part of the United Arab Emirates that surrounds it on land but belongs to Oman, cut off from the rest of the country by Emirati territory. Musandam is limestone folded and shoved upward by the collision of 2 continental plates, then drowned at the edges when sea levels rose after the last ice age. What that leaves is a coastline of steep cliffs and deep flooded valleys running back into the mountains, which is why people who have sailed there call it the fjords, even though it has nothing to do with ice. Between the tip of Musandam and the Iranian shore is the Strait of Hormuz. The United States Energy Information Administration, which publishes the standard reference figures on the world's oil choke points, gives the width at the narrowest point as 21 miles. You'll see other numbers depending on which pair of headlands somebody chose to measure between, and whether they use statute miles or nautical miles. So treat 21 as the widely used working figure rather than a survey constant. Either way, hold the picture. From one shore to the other, less than the distance a fit person could walk in a long day. That's the strait. Now here's the part that changes the whole story. Ships do not get to use 21 miles. Since 1968, traffic through Hormuz has run through a traffic separation scheme, which is the maritime equivalent of a divided highway. It was adopted through the International Maritime Organization, and it is the reason that a place carrying this much tonnage has not turned into a demolition derby. There's an inbound lane and an outbound lane, and between them, a separation zone that nobody is supposed to occupy. The Energy Information Administration puts the usable lane at 2 miles wide in each direction, with a 2-mile buffer between them. 2 miles. That's the operating space. Say you're on the bridge of a very large crude carrier, laden, heading out of the Gulf toward Asia. Your ship is longer than 3 football fields laid end to end. Loaded, she draws around 25 meters, call it 80 feet of steel below the waterline, which means there are large parts of that 21 miles of strait where you physically cannot go, because the water is not deep enough to hold you. The deep channel is generous by world standards, running roughly 60 to 100 meters through the main passage and deeper still on the Omani side. And that generosity is exactly why this route works at all for ships this size. But generosity in depth is not generosity in width. Your lane is 2 miles across, and you are sharing it, in single file and in both directions of a divided scheme, with everything else that has to get through today. Now add the thing that people who have never handled a large vessel consistently underestimate. A loaded, very large crude carrier at service speed does not stop. Not in any sense a driver would recognize. Crash stopping such a ship takes something on the order of a couple of miles, and quite a lot of minutes. And during most of that time, she keeps going more or less where she was already going. Turning is not much better. A large tanker's turning circle is measured in ship lengths, and while she's turning, she's also sliding sideways through the water, which means the path her hull actually sweeps is wider than the path her bow describes. So when a bridge team is running down a 2-mile lane, they aren't steering the way you steer a car. They're managing a decision that has to be made a long time before it takes effect, based on a picture of where they are and where everyone else is, which means position error here has a completely different weight than position error almost anywhere else. Out in the middle of the Indian Ocean, if your navigation system quietly hands you a position that's 3 miles off, the practical consequence is close to zero. You'll notice at some point, you'll correct, and nothing will have happened because there was nothing within 3 miles of you to hit. In the traffic separation scheme at Hormuz, a 3-mile error does not put you slightly off track. It puts you in the opposing lane, or in the separation zone, or on the wrong side of a charted hazard, or inside the territorial waters of a state whose navy is extremely interested in who is inside its territorial waters this week. That last point deserves a moment, because it's the piece that turns a navigation problem into a legal and political one. At the narrowest section, the shipping lanes do not run down the middle. They run through Omani territorial waters, on the southern side, because the deep water is there. That arrangement traces back to the boundary agreed between Iran and Oman in the late 1960s, which drew the line in such a way that the navigable channel falls predominantly on the Omani side. So commercial shipping making the transit is passing through the territorial sea of a sovereign state, Sabri Sari, with no stretch of open high seas in between. Under ordinary rules, a coastal state has real authority over its territorial sea. Hormuz is not ordinary. Because the strait connects 2 areas of high seas or exclusive economic zone and is used for international navigation, it falls under the transit passage regime set out in the United Nations Convention on the Law of the Sea. In the articles running from 37 through 44, transit passage is a stronger right than the innocent passage that applies elsewhere in a territorial sea. Ships and aircraft may proceed without interruption, coastal states may not impede it, and it cannot be suspended. Coastal state regulation is limited to a defined list of concerns: safety of navigation, pollution, fishing, customs, and the like. So on paper, the right to pass is about as protected as any right in the law of the sea, which produces one of the flatter ironies in this entire subject. Nothing in that convention, drafted and signed in an era when a ship's position came from a sextant, a chronometer, a radio direction finder, or a chain of shore-based radio beacons, says anything at all about who may transmit what on the radio frequencies a modern vessel needs in order to know where it is. The legal right to be in the lane is untouchable. The practical ability to know whether you are in the lane is not protected by anything. There's a further constraint the map does not show. Leaving the lane is not a free action. In a normal seaway, if a bridge team loses confidence in its position, the safest move is often to open up, get out of the traffic, find room, slow down, sort it out. At Hormuz, the water on either side of the scheme has been, at various points, the subject of advisories about mines, about restricted zones, about naval activity, about the boundary of somebody's claimed control. In the spring of 2026, regional maritime advisories included mine risk in the vicinity of the traffic separation scheme itself. When the shoulder of the road is worse than the road, you stay on the road, even when you're no longer sure where the road is. Put those together, and you get the first part of the machine, a 21-mile gap, of which 4 miles are usable and split in two. Ships that need 80 feet of water and 2 miles to stop, a route locked into the territorial sea of one state, watched from the shore of another. A legal regime that guarantees your right to be there and says nothing about your ability to find there. And no comfortable place to pull over. That's the container. Now let's look at what's being poured into it. In a normal year, and we should be honest that the phrase normal year is doing some work in this region. The Strait of Hormuz carries about 20 million barrels of crude oil and petroleum liquids a day. That figure comes from the Energy Information Administration's accounting for 2024, and it works out to roughly a fifth of everything the world consumes in petroleum liquids. Not a fifth of what gets exported. A fifth of global consumption, moving through a 4-mile-wide pair of lanes. Alongside the oil, roughly a fifth of the world's liquefied natural gas shipments came out through the same gap, with Qatar accounting for the overwhelming majority of it. Qatari gas has no other exit. There is no pipeline north through Iran, no pipeline west across Saudi Arabia to the Red Sea for that product at anything like that volume. It gets chilled to minus 162 degrees Celsius, which is around minus 260 Fahrenheit, loaded into insulated tanks and driven out through Hormuz. That's the route. There isn't another one. Some crude does have alternatives, and it's worth naming them so the picture stays honest, because no alternatives at all is one of those claims that gets repeated until it hardens. Saudi Arabia operates a pipeline running west across the peninsula to the Red Sea coast. The United Arab Emirates operates one running to Fujairah on the Gulf of Oman side, which by design bypasses the strait entirely. Those exist, and they matter. What they cannot do is absorb the whole flow. Their combined capacity is a fraction of what moves by sea, so for most of the volume, the Energy Information Administration's assessment is blunt. There is no alternative means of leaving the region. Turn all of that from barrels into hulls, and you get something in the range of 130 to 150 vessel transits on an average day, a figure reported in coverage of the current interference and consistent with the traffic densities the traffic separation scheme was built to handle. Crude carriers, product tankers, gas carriers, container ships, bulkers, car carriers, offshore supply vessels, naval traffic, dhows, and fishing craft working the inshore zones. Some of those hulls are among the largest moving objects human beings have ever built. Some are wooden and older than the people steering them. They all have to fit through the same opening, and under the collision regulations, they all have equal claim on the water. Now hold two facts against each other, because the friction between them is where this story actually lives. Fact 1. This is the single most consequential piece of navigable water in the global energy system, and everyone involved knows it. It has been studied, charted, surveyed, patrolled, insured, war-gamed, and modeled more thoroughly than almost any comparable stretch of sea. Fact 2. As of the spring and summer of 2026, the ships making that transit have not been able to fully trust the instrument that tells them where they are. The scale of the disruption is measurable, and it's worth looking at directly, rather than through adjectives. In the first quarter of 2026, crude oil and petroleum liquids moving through the strait fell to about 14.6 million barrels a day, a drop of nearly 30% against the same quarter the year before. In the immediate aftermath of the strikes that opened the crisis in late February, reporting described traffic falling by around 70% almost at once. By the second week of March, coverage citing tracking data and advisory notes described stretches where only a few dozen vessels made the transit across an entire week, against a normal weekly count in the high hundreds. In April, the International Maritime Organization reported roughly 2,000 ships and around 20,000 seafarers caught inside the Gulf, unable or unwilling to make the run out. That last number is the one I'd slow down on, and not because it's large, because of what it's counting. 20,000 people, not passengers, crews. The merchant marine is a working profession staffed disproportionately by seafarers from India, the Philippines, Indonesia, Ukraine, China, and a dozen other countries, on contracts measured in months, in accommodation blocks stacked above an engine room, a very long way from anybody who can help them. When a choke point closes or half closes, they don't go home. They sit at anchor, or they steam in slow circles in a holding area, or they make the transit anyway because the charterer needs the cargo delivered and the master has decided the risk is acceptable. Through the first half of 2026, the crisis reporting recorded seafarers killed and injured aboard commercial vessels in this region. The exact tallies vary between sources, and some individual incidents remain contested, but the fact of casualties among merchant crews is not in dispute, and any account of this subject that treats the strait purely as a line on an energy chart is missing the people standing the watches. I mention this now early because it changes how you should read everything that follows about instruments and signals and decibels. A false position matters because somewhere on a dark bridge, at 3 a.m, a second mate with a coffee going cold is looking at a screen and making a decision about a 2-mile lane on the basis of what that screen says. The wrong entry in somebody's database is the least of it. So we arrive at the obvious question, and it's the right one to ask at this point. How did we get to a place where the entire commercial fleet's answer to "where am I" comes from a single source? Because it did not used to. For most of the history of deep-sea navigation, position came from a chain of independent methods that cross-checked each other and had almost nothing in common. Dead reckoning, known course, known speed, known time elapsed, therefore estimated position, updated continuously, and drifting steadily wrong as currents and wind pushed the ship off the assumption. Celestial observation, a sextant, a horizon, a star, or the sun, a nautical almanac, and an accurate clock, producing a line of position that could be crossed with others to make a fix. Soundings, a lead line or later an echo sounder, matched against charted depth contours, which in some waters is startlingly precise. Bearings on identifiable landmarks, radio direction finding. And from the middle of the 20th century, chains of shore-based transmitters like Decca and Loran, which let a receiver work out its position from timing differences between ground-based stations. Every one of those has weaknesses, dead reckoning drifts. Celestial needs a horizon and a sky, which rules out fog, overcast, and most of the daylight hours for star sights. Soundings need distinctive bottom. Radio chains need to be within range and were never global. But look at what that collection of weaknesses actually gave you. They were uncorrelated. Cloud does not affect an echo sounder. A dead radio beacon does not affect a sextant. Current setting used sideways does not affect a visual bearing on a lighthouse. A navigator working in that world was running several independent systems at once, and when two of them disagreed, the disagreement itself was information. That's not nostalgia. And I'm not about to argue that the old way was better, because it demonstrably killed a lot of people. It's an observation about architecture. The old bridge was a committee. Disagreement was built in. Then, over about 3 decades, the committee was quietly replaced by a single expert witness. Nobody sat down and decided that world shipping should stake its position, keeping on one constellation of satellites. There was no meeting. What happened instead is the ordinary way infrastructure gets built, which is that something worked so much better than the alternatives that the alternatives stopped being maintained, and then one day the alternatives were gone, and nobody had noticed the moment it happened. The global positioning system reached full operational capability in the mid-1990s. Before that, it had already been running well enough that commercial receivers were spreading through the fleet. It offered something that no previous method had ever offered: a continuous position, anywhere on Earth, in any weather, day or night, updated every second, accurate to within a few tens of meters and later a good deal better, requiring no skill from the operator beyond reading a display. A capability that had previously demanded training, judgment, clear weather, and time became a number that was simply always there. You cannot overstate how much that changed. Whole categories of casualty went away. Ships stopped running onto reefs that had been killing ships for centuries. Search and rescue got faster because a vessel in distress could say where it was instead of estimating. Route planning got tighter, fuel burn dropped, schedules got reliable enough to build supply chains on. This was, by any reasonable accounting, one of the great safety improvements in the history of the sea. And then the regulation caught up, as regulation does, and formalized the dependence. Under the International Convention for the Safety of Life at Sea, the regulation known as Chapter 5, Regulation 19, all ships, regardless of size, are required to carry a receiver for a global navigation satellite system or a terrestrial radio navigation system, capable of determining position throughout the intended voyage. In practice, for the world fleet, that means a satellite receiver, because the terrestrial chains that could have satisfied that clause were shut down in most of the world as unnecessary. The United States switched off its LORAN chain at the start of the 2010s. Europe wound down its own. The redundancy was decommissioned because the primary was so good. Around the same period, paper charts went the same way. The electronic chart display and information system, universally called ECDIS, was phased into mandatory carriage across the world fleet through the 2010s, ship type by ship type and tonnage band by tonnage band. An ECDIS does a great deal more than put a chart on a screen. It's a live display that takes a position input and draws your ship on the chart in real time with the planned route, safety contours, alarms for shallow water, alarms for crossing a boundary you told it to watch. It is superb. Bridge teams who have used both will tell you that going back to plotting fixes by hand on paper in confined waters would feel like taking the mirrors off a car. Now follow the wiring, because this is the part that turns a good tool into a systemic risk. That satellite receiver on the mast does not just feed the chart display. Its output is the position input for the automatic identification system, which broadcasts the ship's identity, position, course, and speed over very high-frequency radio, several times a minute, to every other vessel and shore station in range. It feeds the voyage data recorder, the maritime equivalent of a black box. It feeds the digital selective calling function on the radios, which is what transmits your position in a distress alert. It typically feeds the radar's chart overlay and the automatic radar plotting aids calculations of where other ships are heading relative to the ground. On offshore vessels, it feeds dynamic positioning, the system that holds a ship stationary over a wellhead using thrusters. It feeds engine performance monitoring, weather routing, port arrival systems, cargo documentation, emissions reporting, and it does something else that most people outside the field have never thought about. It supplies the time. Satellite navigation is, at bottom, a timing system. The position falls out of the timing. Every satellite carries atomic clocks. The receiver measures the arrival times of signals from several of them, and geometry does the rest, which means the receiver, as a byproduct, has an extremely accurate clock. And once you have an extremely accurate clock available for free, all sorts of equipment quietly starts using it as a reference. That is true on ships, and it's true across the wider world, in power grids, in financial trade timestamping, in mobile phone networks, in broadcast synchronization. Whole industries that would swear they have nothing to do with navigation are, in fact, downstream of it. So here's the architecture we ended up with, stated plainly. A single receiver, taking a single class of signal, from a single direction, feeds the position and the time into essentially every system on the bridge that needs to know either one. It's a beautiful piece of engineering. It's also a choke point, sitting inside a choke point. I want to flag an opinion here, since it's my own and it's relevant to how you weigh the rest. I don't think the fleet was careless. I think the fleet responded rationally to a technology that was, for about 25 years, essentially never wrong. If something never fails, building on top of it counts as good engineering. What we're discussing is a failure of imagination, and specifically the failure to imagine that the reason the thing never failed was that nobody with the means had yet found a reason to attack it. That's a different kind of reliability than the reliability of a well-built engine, and the difference only becomes visible after somebody attacks it. There's one more property of this architecture that matters enormously for what follows, and it's easy to miss. When a mechanical system fails, it usually announces itself. A bearing that's going bad gets hot and makes noise. A hull that's taking water sits down in the stern. A generator that's failing trips a breaker. Engineers call this failing loud, and it's an underrated virtue because a loud failure gets attention. Satellite navigation under attack can fail extremely quietly. The receiver has no way of knowing whether the signals it's hearing came from 12,000 miles up or from a truck on a hillside 8 miles away. It was never designed to check. Nothing in the original civilian signal structure carries any proof of origin. There's no signature, no seal, no way to ask a satellite to prove it's the satellite. The receiver's entire job is to trust the signal and do the arithmetic, and the arithmetic is flawless. Which means that if somebody sends a well-made counterfeit, everything downstream of that receiver, the chart display, the identification broadcast, the black box, the distress function, the radar overlay, will confidently and simultaneously agree on an answer that's wrong. There's no dissent in the system because there's no independent voice left in it. The committee was disbanded. The single expert witness is on the stand, under oath, absolutely certain and lying without knowing it. To understand how a counterfeit can beat the real thing so easily, you have to understand something about the real thing that is quite strange, and that almost nobody who uses satellite navigation every day has ever been told. The signal is unbelievably weak. It's weaker than you can probably picture, and it is weak on purpose. The satellites are about 12,500 miles up. That's medium Earth orbit, roughly halfway to the geostationary belt, and it's high enough that at any given moment, a receiver with a clear view of the sky can see somewhere between 6 and 12 of them. From that distance, each satellite radiates a signal that spreads out across a hemisphere of the planet. By the time it reaches the top of your antenna, the specification for the standard civilian signal on the L1 frequency says the power arriving there is guaranteed to be no less than a level engineer's right, as minus 158.5 decibel watts. That notation hides how small the number is, so let's unwrap it. It works out to roughly 1.5 ten-thousandths of a trillionth of a watt. If that phrase slid past you, good, because it's supposed to. There's no everyday object to compare it with. It's faint enough that describing it in ordinary units produces gibberish. Here's a comparison that actually means something, though. Any electronic receiver generates noise all by itself, simply by being warm. The electrons in its components are jostling around at room temperature, and that jostling produces a hiss across the radio spectrum. It's unavoidable physics, and it sets a floor. Nothing quieter than that hiss can normally be heard, because it's buried in the receiver's own internal weather. For the bandwidth a satellite navigation receiver works in, that thermal noise sits at around minus 130 decibel watts. So the signal is roughly 28.5 decibels below the noise. Turn that out of decibels and into a plain ratio, and you get this. At the moment the satellite signal arrives at your antenna, the receiver's own background hiss carries something like 700 times more power than the signal it's trying to hear. Read that again, because everything else in this story hangs on it. The thing your ship uses to know where it is arrives at the antenna several hundred times quieter than the static the receiver is making by itself, which raises an obvious objection. If it's buried that deep, how does anything work at all? The answer is a trick called spread spectrum, and it's one of the loveliest pieces of engineering in 20th century radio. Instead of concentrating the signal into a narrow slice of frequency, where it would be loud but easy to block, the transmitter deliberately smears it across a wide band by multiplying it with a rapid pseudo-random code. The civilian code runs at 1.023 million chips per second, and it's not actually random. It's a specific, published, entirely predictable sequence unique to each satellite, and every receiver on Earth has a copy of every one of them. So the receiver does this. It generates its own local copy of a satellite's code, and it slides that copy back and forth in time against whatever it's hearing on the antenna, looking for the moment when the two line up. When they do, all the energy that was smeared across the band collapses back into a spike. Everything that does not match the code, including the thermal hiss and most ordinary interference, does not collapse, because random noise does not correlate with a known sequence. The signal comes back out of the mud. The alignment point tells the receiver exactly how long the signal took to arrive, which, multiplied by the speed of light, gives a distance. Do that to 4 satellites, and you have solved for 3 coordinates and the time. That process, called despreading, buys back roughly a factor of 1,000 or more against the noise, which is precisely how something 700 times quieter than the static becomes a usable measurement. There's a piece of history hiding inside that idea that I find almost too neat to be true, and it's worth the detour because it explains the design philosophy. The broad family of techniques that spread a signal across a wide band to make it hard to jam has an origin story involving a film actress and an avant-garde composer. In 1942, Hedy Lamarr, who was at that point a household name in Hollywood, and George Antheil, a composer best known for a piece scored partly for synchronized player pianos, were granted a United States patent for a secret communication system. Their idea was to make a radio-guided torpedo resistant to jamming by having the transmitter and receiver hop rapidly between frequencies in a shared, prearranged pattern. The synchronization mechanism they proposed was borrowed straight from the perforated paper rolls that drove player pianos. The Navy did not take it up at the time. The underlying principle, that you defeat interference by refusing to sit still on one frequency and by hiding the signal in a pattern only the intended receiver knows, became foundational to military and later civilian radio. Satellite navigation uses a different member of that family. It does not hop between frequencies. It stays put and spreads its energy thinly across a wide band using that pseudo-random code. But the design intent is a direct descendant. Survive interference by refusing to be a loud, narrow, easy target. And it works. It works so well that the system was built to arrive below the noise floor as a matter of course, which in turn let the satellites use modest transmitters run for decades on solar panels and serve an entire planet at once. The faintness of the signal is something the whole architecture was designed around from the beginning. Now watch what happens when somebody local decides to be louder. Radio power falls off with the square of distance. Double the distance, quarter the power. That relationship is merciless over long ranges, and satellite navigation operates at very long range indeed. Take a rough illustration. Ignore antenna patterns, ignore atmospheric effects, ignore the curvature of the problem, and just do the geometry. A satellite is 12,500 miles from your antenna. A transmitter sitting on a headland is 12.5 miles from your antenna. The distance ratio is 1,000 to 1. Square it. And the closer transmitter has a raw advantage of 1,000,000 to 1 in delivered power for every watt it radiates. Give the satellite every benefit. Assume it's transmitting several hundred times more power than the little transmitter on the headland. Run the arithmetic anyway, and the headland still wins by a factor in the thousands. That's the whole vulnerability in one line. Satellite navigation is superbly engineered. The trouble is that the physics of distance means anything on the ground, anywhere near you, with a modest amount of power and an antenna, is enormously louder at your receiver than a spacecraft 12,000 miles away, and no amount of clever coding in orbit changes the inverse square law. The equipment required is not exotic. Devices capable of denying satellite navigation over a useful radius are small, cheap, and widely available, which is why they turn up in the hands of truck drivers trying to defeat fleet tracking, and in criminal cargo theft, as well as in the inventories of militaries. Scaling that up to cover a strait takes more power and better antennas, but it's a difference of degree. So we now have 3 of the 4 parts of the machine. A 4-mile operating corridor with ships that need miles to stop. A fifth of the world's oil and a fifth of its liquefied gas funneled through it, and a navigation signal that is, by design, several hundred times fainter than static by the time it arrives. The 4th part is what happens when somebody points a transmitter at that corridor. And there are 2 very different ways to do it, which produce 2 very different experiences on the bridge, and the difference between them is the difference between a problem and a trap. Jamming is the crude one, and I mean crude as a description of method rather than an insult to its effectiveness. The idea is simply to raise the noise floor. Remember the trick that makes the whole system work. The receiver recovers a signal buried 700 times below the static by correlating against a known code. That trick has a budget. It buys back a certain amount of margin and no more. So if you flood the frequency band with enough power, you push the noise up past what the correlation can dig through, and the receiver stops being able to find the satellites at all. It's not deceived. It's deafened. On the bridge, this announces itself. The receiver loses lock, one satellite at a time or all at once, and starts throwing alarms. The chart display gets a position source alarm and either freezes the vessel symbol, where it last had a fix, or switches to dead reckoning, drawing the ship's assumed track forward from the last known position, using gyro heading and speed through the water. The automatic identification system stops transmitting a valid position, or transmits a default value, which means the ship effectively goes dark to everyone relying on that broadcast to see it. The voyage data recorder logs a gap. The distress function on the radios loses the position it would otherwise attach to an alert. And the crew knows immediately. That's the important part. There's a design principle in safety engineering about failing loud, and jamming, whatever else you want to say about it, fails loud. Within seconds of the interference starting, the bridge team is looking at alarms, And alarms trigger training. You stop trusting the chart position. You go to the radar. You take ranges and bearings to charted objects. You look out the window. You get the master up if he's not already up. Nobody is being fooled about anything. That does not make it harmless. And I want to be precise about why, because it's not the obvious reason. The obvious reason would be that the ship no longer knows where it is. In a 2-mile lane, that's serious. But a competent bridge team on a well-found ship in coastal waters is not helpless without satellites. The radar still works. The gyro still works. The echo sounder still works. The Musandam Peninsula, as it happens, is superb radar country. Steep limestone cliffs dropping into deep water, throwback hard, unambiguous returns, and there are charted islands and headlands with distinctive shapes at intervals through the transit. A navigator who can take a couple of radar ranges to charted features and cross them will get a fix good enough to run the lane on. That skill was standard for generations, and it is still taught. The real problem is what jamming does to everybody else. Think about what makes a narrow lane with heavy traffic survivable. Each ship knowing its own position is only half of it. The half that does the real work is every ship knowing where all the others are, continuously, without having to guess. That comes from radar, from the automatic radar plotting aid computing closest point of approach, and increasingly from the identification broadcasts that let a bridge see on the chart a labeled symbol for every ship in the area with its name, its heading, its speed, and its rate of turn. Jam the area, and that shared picture degrades for everyone simultaneously. Ship A's identification broadcast goes dark or goes wrong. Ship B, 3 miles astern, loses the symbol that was telling her what Ship A intended. Ship C, coming the other way in the opposing lane, loses both. Shore-based vessel traffic services lose the plot they use to spot developing problems before the ships involved notice them. What had been a coordinated flow becomes a set of independent guesses, all being made by people who cannot see very far in the dark and cannot stop. Radar picks up a lot of that slack, and radar is very good. But radar shows you an echo, not an intention. It cannot tell you that the contact 2 points off your starboard bow is a laden gas carrier with a restricted ability to maneuver, or that she has just requested a course alteration from traffic control, or what her name is, so you can call her on the radio. Losing the identification layer does not blind a bridge. It makes every encounter slower to interpret and more dependent on the radio, at the exact moment when the radio is busy. Now put numbers on how common this has become, because the scale is the thing that turns an incident into a condition. Reporting drawn from Windward's monitoring during the late February and March period of 2026 described more than 1,700 satellite navigation interference events recorded across the affected area. Within that, more than 900 jamming events were logged in Emirati waters around Dubai and Fujairah, affecting over 600 vessels, with a further 190 or more events in the Gulf of Oman, showing the circular tracks and position jumps that indicate something more than simple denial. In a separate 24-hour count, more than 1,100 vessels were affected across the Middle East Gulf. The Joint Maritime Information Center's advisory note in that same period logged more than 600 disruption events in a single day. Those figures come from commercial monitoring and from a multinational information center rather than from a single government, and different providers count events differently, so I'd treat them as consistent orders of magnitude rather than as an audited census. The picture they agree on is the point. This is happening to a large share of everything that moves through the region, most days. It's also worth saying clearly that Hormuz is not a special case in kind, only in consequence. The United States Coast Guard's Navigation Center, which collects satellite navigation problem reports from mariners, has logged disruptions in the Eastern Mediterranean, the Black Sea, the Red Sea, the Baltic, and the coastal waters of China. Through 2024, ships and offshore support vessels reported jamming across several of those areas. Aviation has the same problem, and in some ways a worse one. Interference affecting aircraft navigation rose sharply through 2024, and there have been high-profile cases, including an aircraft carrying the president of the European Commission diverting after interference during an approach. So the technique is spreading, the equipment is available, and the underlying vulnerability is universal, because it's a property of physics rather than of any particular country's equipment. What makes Hormuz the place where this stops being an inconvenience and becomes a navigation emergency is everything we established earlier. 2-mile lanes, ships that need miles to stop, 150 transits a day, nowhere safe to pull over. Take any of those away and jamming is a nuisance you ride out. Put them together, and a degraded picture in a crowded corridor becomes the setup for exactly the kind of casualty the traffic separation scheme was invented to prevent. But jamming, for all of that, is the version where everyone at least knows what's happening. The other version is worse in a way that's difficult to convey until you've thought carefully about what it would actually be like. Spoofing does not deafen the receiver. It talks to it. Instead of flooding the band with noise, a spoofer generates counterfeit versions of the satellite signals themselves. It produces the right codes, on the right frequency, with the right structure, arriving with plausible timing. The receiver, which has no mechanism for asking a signal to prove where it came from, finds these fakes easier to hear than the genuine article, because the fakes are coming from a few miles away and the genuine article is coming from 12,500. It locks on. It does the arithmetic. It produces a position with every appearance of a healthy fix. Todd Humphreys, who runs the radio navigation laboratory at the University of Texas at Austin and who built the first publicly acknowledged civilian spoofing device back in 2008, put the mechanism about as clearly as it can be put. A receiver, he explains, is listening for a handful of separate satellites at once. A spoofer pretends to be all of those signals at the same time, and it comes from a single antenna. That single antenna detail is the fingerprint, and later on it becomes the basis for one of the defenses, so keep it somewhere handy. Real satellite signals arrive from scattered directions across the sky. Counterfeit ones, in the simple case, all arrive from one bearing because they all come out of the same transmitter. Humphrey's laboratory demonstrated the practical conjugal consequence in a controlled experiment in the Mediterranean in 2013, working with the owners and crew of a large private yacht who had agreed to the test. His team broadcast counterfeit signals from aboard the vessel, gradually overpowered the genuine ones, and induced the ship's navigation system to report a position that was steadily and quietly wrong. The autopilot, doing exactly what it was told, corrected toward a track that existed only in the counterfeit picture. The crew on the bridge saw a chart display that looked completely normal. The part worth pausing on is that last sentence. The whole thing looks like nothing while it happens. There are two broad ways to do it, and they leave very different traces. The blunt version simply overpowers everything and asserts a location. The receiver's position jumps. 1 second the ship is where it actually is. The next second it's 40 miles away, sitting on a runway. That version is obvious to anyone paying attention because ships do not teleport, and it's the version that produces the screenshots that circulate. Fleets of tankers apparently parked at airports, container ships drawing tracks across the desert, vessels tracing neat circles over land. The subtle version is called carry-off, and it's the one that keeps navigators awake. A carry-off spoofer first synchronizes with the genuine signals, matching their timing so closely that the receiver notices no discontinuity at all. Then it raises its power slightly and begins, very slowly, to shift the timing. The receiver follows because from its point of view, nothing has happened except that the satellites appear to have moved a hair. The computed position starts drifting away from the true one at a rate of a few meters a minute. On the chart display, the ship's track stays smooth and continuous. The drift looks exactly like the effect of a current setting the vessel gently off her course. which is an entirely ordinary thing for a ship to experience, and an entirely ordinary thing for a navigator to correct for without a second thought. And because the drift is smooth, it can slip past the receiver's own internal sanity checking. Modern receivers run a function called Receiver Autonomous Integrity Monitoring, which uses the redundancy of extra satellites to spot a measurement that disagrees with the others. It's useful against a single faulty satellite. It's much less useful against a coherent counterfeit picture in which all the measurements have been shifted together, in step, so that they remain perfectly consistent with one another while being consistently wrong. Consistency is the trap. The reason a bridge team trusts a fix is that everything agrees. In a spoofed environment, everything still agrees, because everything is drinking from the same poisoned well. The chart display agrees with the identification broadcast, agrees with the black box, agrees with the radar overlay. And they all agree because they are all fed by the receiver that has been captured. Now scale it up, because a spoofer does not target a ship. It illuminates an area. Anything inside the transmission footprint that's listening on that frequency gets the same counterfeit picture, which is why the observable signature shows up as a whole population of vessels behaving strangely in the same way, at the same time, in the same place. Analysts watching the Gulf during the current crisis have described exactly that. Clusters of vessels near the Emirati coast, whose reported positions form long, straight lines heading toward the strait, lines that no real ship was following. Windward's monitoring described positions displaced onto airports, onto inland locations in Iran and in the Gulf states, and across a nuclear power plant. Off Ras Al Khaimah, coverage described the reported tracks bunching into linear patterns inconsistent with any actual navigation. Once you know what you're looking for, that pattern is unmistakable. Ships are not organized. Real traffic, plotted over hours, looks like traffic. A scatter of vessels doing individual things at individual speeds. Spoofed traffic looks tidy. It falls into lines and rings and stacks. Reality is messy, and the absence of mess is the tell. There's one more property of this that changes the strategic picture entirely. The technique has a genealogy that's now more than a decade old, and it has spread. Reporting cited by Scientific American describes Russian use of spoofing around sites associated with the presidency going back to 2016, and Israeli use of spoofing in 2024 to complicate the guidance of incoming threats. Both of those are defensive rationales, and both illustrate a hard fact about this weapon. You cannot aim it narrowly. A spoofer trying to protect a stretch of coastline from a guided munition is, in the same act, feeding false positions to every merchant ship, fishing boat, and airliner in its footprint. The tanker on the airport apron is very often not the target. It's the weather. Against that, the merchant fleet is carrying receivers that were never designed to argue back. Humphreys has pointed out that the satellite navigation technology typically installed aboard a commercial ship runs something on the order of 15 years behind the state-of-the-art. That's the ordinary economics of a capital asset, with a 25-year service life and a bridge refit cycle measured in decades, and it has very little to do with competence. Nobody rips out a working navigation suite because a better one exists. The result is a global fleet whose defensive equipment is, on average, a technology generation and a half behind the offensive equipment now pointed at it, which is why the ships can no longer trust their position is a precise statement and not a dramatic one. The instrument still works. What it stopped being is a source of truth. It's now a source of testimony, and testimony has to be corroborated. Before we get to how it gets corroborated, though, there's a discipline problem to deal with, because if you accept everything I've just described, there's an enormous temptation waiting for you, and most coverage of this subject falls straight into it. The temptation is this. Once you know that spoofing exists, is cheap, is happening across this exact stretch of water on most days, and leaves no trace on the bridge, then every collision, every grounding, every ship that ends up somewhere it should not be starts to look like evidence of it. That instinct is understandable, and it's wrong often enough to be dangerous. Ships have been colliding and running aground for as long as there have been ships, for reasons that owe nothing whatsoever to radio. If you attribute every casualty to interference, you achieve two bad things at once. You overstate a real problem to the point where serious people stop listening to you, and you quietly excuse the ordinary failures of watchkeeping, fatigue management, and passage planning that remain, by a wide margin, the leading causes of maritime accidents. So let's do the discipline properly. With a case where the temptation was strongest. Just after midnight on the 17th of June, 2025, about 15 nautical miles off Fujairah, on the Gulf of Oman side of the peninsula, two tankers collided. The Front Eagle, a very large crude carrier running south at around 13 knots with roughly 2 million barrels of Iraqi crude bound for China, made a turn to starboard and struck the port quarter of the Adelan, a Suezmax tanker. Fire broke out on the deck of the Front Eagle and was extinguished. All 24 crew aboard the Adelan were taken off and landed at Khor Fakkan. No injuries were reported aboard the Front Eagle, and no pollution was reported at the time. The timing could hardly have been more suggestive. This was in the middle of a period when windwards monitoring indicated something approaching 1,000 vessels in the Gulf had been affected by electronic interference. A prominent maritime commentator, the historian Sal Mercogliano, raised publicly the possibility that spoofing had contributed to the collision, perhaps by feeding a false picture to the navigation system or the autopilot. Within hours, that possibility was circulating widely, as though it were an established finding. Here's what the parties with access to the vessels actually said. Frontline, which owns the Front Eagle, stated that the incident was a navigational accident and was not connected to the regional conflict. The Emirati authorities, through the Ministry of Energy and Infrastructure, attributed the collision to navigational misjudgment by one of the vessels. Two things are true at the same time here, and holding both is the whole skill. Widespread electronic interference in that region during that period is well documented, and the owner and the coastal state, both of whom had access to information that outside observers did not, concluded that this particular collision came down to a navigational decision. Neither of those statements cancels the other. What follows from them is a rule. This collision is not a load-bearing piece of evidence for the spoofing story, and building the argument on it would be building on sand. There's an older case that makes the same point from the opposite direction, and it's instructive because the speculation there was even more confident. In January of 2016, two United States Navy riverine command boats strayed into Iranian territorial waters near Farsi Island in the Gulf, and their 10 crew were detained for a night before being released. Almost immediately, a theory took hold that the boat's navigation had been interfered with, that the Americans had been electronically lured. Iranian officials at the time made statements about the boat's equipment. It made a compelling story, and it fit everything people already believed about the region's electronic warfare capability. The United States Navy investigated its own incident and published the results that summer. The investigation examined whether the boat's technology had been tampered with and concluded that it had not. The cause it identified was a chain of human failures, inadequate mission planning, poor risk management, leadership shortfalls. Crews who took an unauthorized shortcut because they were behind schedule, equipment problems that were known about and sailed with anyway. The Navy's own language about operational discipline was unsparing. Whatever else that incident was, the service that lost the boats did not find a technological villain, and it looked hard. I bring that up because it's the cleanest available demonstration that the presence of capability does not establish the use of capability in any given case, and that an organization with every incentive to blame an adversary can look at the evidence and conclude otherwise. There's a third category too, and it's the least glamorous and probably the most common. Equipment simply goes wrong. A satellite navigation antenna sits at the top of a mast in salt air for years. Connectors corrode and cable runs chafe. Signals bounce off the superstructure and off stacks of steel containers and arrive at the antenna twice, by two different path lengths, which is called multipath, and which degrades a fix in ways that look mildly strange rather than obviously broken. Chart datums can mismatch, so that a perfectly correct position gets plotted onto a chart drawn to a different reference and lands a few hundred meters from where it belongs. Software has bugs. Settings get changed. Something that looks exactly like a spoofing signature at a distance is quite often a loose plug. The professional guidance reflects this. When mariners are told to suspect interference, they're also told how to rule out the mundane explanations first, because the response to a failed antenna is different from the response to a hostile transmitter, and getting that wrong wastes the one resource a bridge team in a narrow channel does not have, which is time. That's what makes attribution in this field so much harder than people expect. Radio interference is transient, unless somebody happened to be recording the radio spectrum at that place, and that moment with equipment capable of characterizing the signal and determining a bearing to it. The evidence is simply gone the instant the transmitter stops. A ship can report that it lost position for 3 hours in a given area, and that report is valuable, and it does not tell you what was transmitting, from where, at what power, or why. Working backward from an effect on a receiver to a physical transmitter on a coastline requires either direction-finding equipment in the area at the time, or enough reports from enough vessels at enough different positions that you can triangulate a footprint. Both happen. Neither is routine. That's why the honest version of this story contains a great deal of "we know the effect." We can characterize the pattern, and the source is not established. It's also why you should be suspicious of any account that tells you exactly who transmitted what, with confidence, without naming who determined that and how. We'll come back to what has actually been attributed, and by whom, once we've dealt with the more immediate question. Because whatever is causing it, there's a bridge team in the middle of it right now, and they have to get the ship through. Before we get to the bridge, there's a second failure running in parallel, and it's the one that lets the rest of the world see what's happening. It also explains why those images of tankers on runways exist at all. Ships broadcast their own positions, continuously, automatically, and to anyone with a receiver. The automatic identification system was introduced as a collision avoidance tool and made mandatory under the same safety convention chapter we met earlier. Cargo ships of 300 gross tons and upwards on international voyages carry it. Cargo ships of 500 gross tons and upwards on domestic voyages carry it, and all passenger ships carry it regardless of size. It transmits on two very high-frequency maritime channels. While a vessel is underway, it sends dynamic data every few seconds, as often as every 2 seconds for a fast ship making a turn, and static data about the ship's identity, dimensions, cargo type, and destination every few minutes. It was designed to be heard over the horizon by other ships and by shore stations. What nobody quite anticipated in the 1990s when the standards were being written is that satellite receivers would eventually be able to pick those broadcasts up from orbit, which turned a local anti-collision aid into a global surveillance layer. Today, an entire industry rests on it. Insurers use it to verify where a hull actually went. Commodity traders use it to estimate flows before the official statistics arrive. Sanctions compliance teams use it to check whether a cargo touched a prohibited port. Port authorities use it to plan berths. Search and rescue coordinators use it to find the nearest ship to a casualty. And here is the crucial structural fact. The position and identification transmitter broadcasts come straight out of the ship's satellite navigation receiver. It does no measuring of its own. It repeats what it's handed. Follow that through. Spoof a ship, and you do not merely deceive that ship. You conscript it. It will take the false position it has been given and broadcast it several times a minute, over the horizon, and up to satellites, in complete good faith, with its real name and its real dimensions and its real cargo type attached. It becomes an unwitting transmitter of the lie, and everyone downstream of that broadcast, other vessels, coastal authorities, insurers, analysts, navies, receives a message that is correctly formatted, properly addressed, cryptographically unremarkable, and entirely false. That's why the visible symptom of this problem is a picture rather than a report. Nobody drew those tankers on the airport apron. That image is a plot of what the ships themselves reported, in their own voice, with their own names attached. Now add a complication that makes the analytical problem properly nasty because in this particular region, both things are happening at once. There's a completely separate practice, confusingly given a similar name, called identification system spoofing, in which the falsification is done deliberately by the ship or its operator. The transmitter is fed a fabricated identity, or a fabricated position, or is switched off entirely during a segment of a voyage. This has been standard tradecraft for years among vessels moving sanctioned cargoes, among fleets engaged in illegal fishing, and among operators who would prefer that a particular ship-to-ship transfer at a particular anchorage go unrecorded. The so-called dark fleet, the aging tankers that move sanctioned oil outside mainstream insurance and inspection regimes, operates heavily in and around this region, and manipulating its own broadcast is part of how it works. So in the same few hundred square miles of sea, you now have three populations mixed together on the same screen. Ships broadcasting true positions, ships broadcasting false positions because their receivers were captured and they do not know it, and ships broadcasting false positions because somebody aboard wanted them to. From the outside, at a distance, those look similar, and separating them is now a real branch of analytical work, which produces a consequence I would not have predicted before looking into this. A navigation problem has become a data problem for a whole set of industries with no direct interest in navigation. The insurance underwriter pricing a voyage, the trader estimating how much crude actually left the Gulf last week, the compliance officer certifying that a cargo is clean, the analyst counting whether traffic through the strait is recovering, all of them are reading a feed that has been degraded at the source. Coverage during the crisis has made this point repeatedly. The strait stopped being purely a military and physical problem and became a problem of knowing what is true. The degradation goes further still because a meaningful share of vessels responded to the danger by shutting their transmitters off entirely. Advisory reporting through the middle of 2026 described a notable portion of transits being made with the identification system switched off, a deliberate choice by masters and companies who had concluded that broadcasting a name, a cargo type, and a position into a contested strait carried its own risk. That's a defensible decision, and it removes another slice of the shared picture. Picture the resulting screen from the bridge of a ship in the outbound lane. Some of the symbols around you are real ships in the position shown. Some are real ships in the wrong positions. Some are real ships showing no symbol at all. And nothing on the display distinguishes the three. Radar cuts through most of that, and thank goodness it does. Because radar measures the world directly. It sends out a pulse, it times the echo, and it does not care what anybody claims. A target on radar is a thing that reflected energy. That's why radar is the anchor of the whole recovery procedure we're about to get into. There's one last consequence of the identification layer failing that almost nobody thinks about until it matters, and it's a legal one. Every ship of any size carries a voyage data recorder. After a casualty, investigators pull it, and it gives them the ship's track, her headings, her engine orders, her rudder angles, the audio from the bridge, the radar image. It's the closest thing the industry has to a flight recorder, and it's the backbone of almost every serious accident investigation. The track it recorded came from the satellite receiver, so if a ship is involved in a casualty while her receiver is being spoofed, the recorder faithfully preserves the false position. The investigation opens with a document that is authoritative in form and wrong in substance, and the burden falls on the investigators to notice and then to reconstruct the true track from radar imagery, from engine and rudder logs, from the recorded bridge audio, from other vessels' accounts. That is possible. It's also slow, expensive, and dependent on somebody thinking to question the one file everybody normally treats as ground truth. Which is a decent summary of the whole subject, actually. The instruments never stopped producing answers. Every one of those answers now needs a second opinion before anyone can act on it. So how do you check? That's the next piece, and it turns out the geography that makes this strait so dangerous is also, in one specific and rather elegant respect, the thing that saves it. Musandam is, from a radar operator's point of view, close to ideal terrain. The peninsula is limestone, pushed up steeply, and eroded into a coastline of sheer faces and deep inlets, with deep water running right up to the rock. That combination does something specific for a ship's radar. A low, sandy, gently shelving coast, of the kind you find along much of the southern Gulf, returns a weak and ambiguous echo, and the waterline you see on the screen may sit some distance from the waterline on the chart. A cliff standing 1,000 feet out of deep water returns a hard, bright, sharply defined edge that corresponds closely to the charted feature. Add the scattered islets and rocks off the tip, charted, isolated, and unmistakable, and you have a stretch of coast that gives a navigator exactly what a navigator wants: unambiguous objects at known positions. I find that satisfying, and not only for aesthetic reasons. The same tectonic history that squeezed the Gulf down to a 21-mile gap and forced the world's oil through it is the history that made the southern shore into a wall of hard radar targets. The geography that creates the danger supplies most of the cure. So here's what a bridge team actually does when the position stops being trustworthy. I want to describe it as practice rather than as instruction, because real procedures depend on the ship, the equipment fit, the company's standing orders, and the specific situation, and a half-remembered rule is worse than none. Professional guidance on this exists. It's detailed, and it's written by people who know the ship in front of them. The first problem is noticing. Under jamming, that's handed to you by the alarms. Under spoofing, it has to be dug out, and the tells are all comparisons between things that ought to agree and no longer do. Speed over the ground, which the satellite receiver calculates, against speed through the water, which comes from a completely independent instrument in the hull. Those two differ in real life because current exists, and the difference is normally small and slowly varying. A sudden change with no plausible tidal explanation is a flag. Course over the ground against gyro heading. Again, a real difference exists because a ship crabs sideways in a current or a crosswind. A drift angle that starts growing for no reason is a flag. The reported accuracy figures the receiver itself publishes, which spike when the geometry or the signal quality degrades. The radar overlay against the chart. This is the big one. If the chart display is drawing the coastline in one place, and the radar is painting it 2 or 3 miles away, something is wrong. And it is not the cliff that moved. Displacements of that order have been documented during interference in this region. Parallel index lines, which are a technique where you draw a line on the radar at a set distance from a fixed object and watch whether your echo tracks along it. When the index starts wandering off, you've got a discrepancy. The echo sounder against the charted depth. This one is old and blunt and lovely. The sea floor does not lie and cannot be transmitted at you. If the chart says you should be in 60 meters and the sounder says 30, one of those is wrong and it isn't the sea floor. And on ships fitted with 2 independent electronic position fixing systems, the position difference alarm, which does precisely what the name says. None of those individually proves anything. Anyone could be an instrument fault. Together, they build a case, and the case is what lets a watch officer make the call that everything else depends on. because the hardest part of this entire situation has very little to do with equipment. It's the decision to disbelieve a working display. Human factors researchers have a name for the tendency, automation bias, and it's remarkably robust across professions. When a machine that has been right 10,000 times in a row tells you something, and your own perception says otherwise, the pull toward the machine is enormous, and it gets stronger the more tired you are, and the more the machine has earned. A satellite navigation receiver on a merchant ship has earned a great deal. Most of the officers on watch today qualified in a world where that position was simply correct, always, and where the training emphasis was on interpreting the display rather than on doubting it. So the real skill being asked for is a kind of professional stubbornness to look at a screen showing a clean, stable, plausible position with no alarms of any kind and treat it as a claim requiring corroboration. That's a change in the relationship between a person and an instrument, and changing a relationship is much harder than changing a procedure. Once the call is made, the response is old-fashioned in the best sense. Fixes come from radar ranges and bearings to charted objects, with ranges carrying more weight than bearings, because a radar measures distance more precisely than it measures direction. Visual bearings, where there's something to see. Transits, where two charted objects line up and give you a line of position for free with no instrument at all. Depth contours from the sounder. The chart display can be told a manually entered fix, a function that has been required in these systems since 2009. And the dead reckoning origin can be reset from that fix, so the automatic track picks up from something real. And one more move, which is the most important of all and the least obvious. Take the ship off track control and steer her by hand. Modern autopilots can be run in a mode where the ship follows a planned route, comparing her satellite position against the intended track and applying rudder to close the gap. It's efficient, it's precise, and in a spoofed environment, it's the mechanism by which a false position becomes a real course change. Feed a carry-off spoof into a track controller, and the controller will obediently and steadily steer the ship away from where she should be, in order to reach where the counterfeit says she is not. The ship works hard, competently, and in the wrong direction. Break that loop by putting a helmsman on the wheel and steering headings from the gyro compass, and the spoof loses its grip on the rudder. A gyro compass finds north from the rotation of the Earth. There's no signal to imitate. Nobody can transmit at it. That's the shape of the answer. And you can see the logic running through all of it. Everything in the recovery kit shares one property. It either measures the physical world directly, like radar and the sounder and the eye, or it derives direction from physics that no transmitter can reach, like the gyro. The response to an attack on a shared external signal is to fall back on things that are local, physical, and mute. The cost is workload, and it's substantial. Manual fixing in confined waters means somebody working the radar and the chart more or less continuously. That's a person who is not doing anything else, on a bridge that in the modern merchant fleet is not lavishly staffed, in a transit that may last many hours, in a region where the crew has other things to worry about. Fatigue is a documented factor in a large share of navigational casualties in normal conditions. Adding a permanent manual workload to a high-stress passage does not make that better. So the ship gets through. Usually the ship gets through. But something has changed in what it costs to get through. And that cost has started showing up in places a long way from the bridge. There's an apparatus for knowing about this, and it's worth understanding because it explains both what we can say confidently and why certain questions stay open. At the bottom of it are the mariners themselves. The United States Coast Guard's Navigation Center runs a reporting channel for satellite navigation problems, where a ship can log what it experienced, where, when, and for how long. Those reports accumulate, and the pattern across many of them is what turns anecdote into a map. Over recent years, the center's logs have filled up with the same handful of places: the waters off China, the Baltic approaches, the Black Sea, the Red Sea, the eastern end of the Mediterranean, the Gulf. Notice what that list has in common. Alongside that sit the regional bodies. United Kingdom Maritime Trade Operations, based in the Gulf, acts as the point of contact between merchant shipping and military forces in the area, receives incident reports, and publishes advisories. The Joint Maritime Information Center produces advisory notes with structured assessments and counts of incidents, which is where those daily disruption tallies come from. The European Union maintains a maritime security center covering the Indian Ocean region. The NATO Shipping Center issues its own guidance. The United States Maritime Administration publishes advisories for American-flagged and American-owned vessels. Flag states issue circulars to the ships on their registers, and several did so specifically about spoofing through 2025. Class societies, protection and indemnity clubs, and hull underwriters all publish their own guidance, partly out of duty, and partly because they will be paying if it goes wrong. Above all of that sits the International Maritime Organization, which has been pushing this issue harder as the numbers climbed. Its Maritime Safety Committee circulated guidance urging member states to take the actions necessary to minimize interference originating from their own territory, which is a legal obligation those states already carry under the International Telecommunication Union's radio regulations. That's the point of law worth holding on to. Satellite radio navigation is designated a safety service, and causing harmful interference to a safety service is prohibited under the international radio rules that essentially every state has signed. There's also standing guidance on how position, navigation, and timing data should be processed and cross-checked aboard ship. And the organization has issued joint statements with the civil aviation and telecommunications bodies, urging states to protect satellite navigation from interference, which is diplomatic language for asking countries to stop. That's a lot of institutional machinery. Notice what it can and cannot do. It can collect, publish, warn, advise, standardize, and appeal. It cannot switch off a transmitter on a coastline belonging to a sovereign state, and it has no enforcement arm that could. Now, attribution. This is where the discipline earns its keep, and I'd rather leave you with an honest gap than a satisfying story. The reporting on the current period does contain attribution, and it comes with varying degrees of authority. Technical trade coverage of the crisis has pointed to Iranian naval exercises and Iranian electronic warfare activity as sources of interference in the Gulf, and has also pointed to the air campaign being conducted against Iran, since electronic warfare is a normal part of such operations and does not stop at a border. American officials have been quoted in reporting expressing the view that interference affecting shipping in the Gulf is associated with Iranian activity. Analysts studying the geometry of the false positions have noted that many of the displaced tracks converge on locations inside Iran, which is at least consistent with transmitters on that coast, since a spoofer that wants to protect a site frequently asserts a false position at or near that site. Set against that, several things have to be said plainly. Multiple parties operate electronic warfare equipment in and around this region simultaneously, and have done for years. Interference affecting merchant ships is very often a byproduct of somebody protecting something else. A system defending a coastline, a port, a refinery, or a fleet against satellite-guided weapons or against drones works by corrupting the navigation of anything in its footprint. And a tanker in the lane is inside that footprint whether or not anyone intended it to be. Reporting has described spoofing being used defensively by more than one state in this broader region in recent years, including by Israel in 2024 against incoming threats, which produced exactly this kind of civilian collateral effect. Second, the technical work of tying a specific interference event to a specific transmitter requires measurements that are almost never made at the moment they would be needed. You would want calibrated receivers with directional antennas at multiple known locations, recording simultaneously so that bearings could be crossed. Navies have equipment like that and do not, as a rule, publish what it tells them. Third, and this is the plain statement, as far as the public record goes, no formal investigation has published a finding naming who transmitted what, from where, in any of the specific incidents affecting merchant shipping in the Strait during this period. Governments have made accusations. Analysts have offered assessments with stated confidence levels. No party has claimed responsibility for interfering with commercial navigation, which is unsurprising, since doing so would amount to admitting a breach of the radio regulations and inviting a set of legal consequences nobody wants. So the honest formulation, the one I'd defend, is this: that interference is occurring, is established beyond argument. Its scale is measured by several independent commercial and multinational monitors whose numbers broadly agree. Its geographic footprint is mappable. Its technical character, jamming here, spoofing there, carry off in some cases, is identifiable from the signatures. Its source, in the sense of a named party operating a named transmitter at a named site, is not established in public, and anyone who tells you otherwise is going further than the evidence. There's a neat piece of detective work worth mentioning here, because it shows how the footprint gets mapped without anyone needing access to classified data. Aircraft, like ships, broadcast their positions through a system called automatic dependent surveillance. Unlike ships, they also broadcast a self-assessment of how good they think their navigation currently is, a set of integrity and accuracy figures that the avionics compute continuously. When an aircraft flies into a region where satellite navigation is being denied, those figures collapse, and the aircraft says so in the clear to anyone listening. Enthusiasts and researchers operating networks of ground receivers have used exactly that to build daily maps of interference across the world, showing zones where aircraft consistently report degraded navigation. It's an elegant inversion. The interference cannot be seen directly, so you map it by watching where instruments admit they're struggling, which is roughly what the maritime world has had to learn to do as well. You cannot see the transmitter. You can see its shadow. So let's put the machine together and run it. Because the interesting part is what the components do to each other. Start with the property that makes a choke point a choke point. Everything that needs to get through is in the same place at the same time. That's the definition. In open ocean, 150 ships a day would be invisible to each other, scattered across thousands of square miles, most of them never coming within radar range of another vessel for days at a stretch. Compress those same 150 into a 4-mile wide corridor, and every one of them is continuously within a few miles of several others. Now degrade the position, keeping across that whole corridor at once, which is exactly what an area effect like jamming or spoofing does. All 150 degrade together, inside the same few miles, within the same few minutes. Each of them becomes a hazard to the others. Each is now working harder and slower to establish its own position, and each of which has partly lost the automated picture that told it what the others were doing. That's the first compounding effect. And it's the one that separates this from an ordinary equipment failure. A single ship with a broken receiver in a working traffic scheme is a manageable problem because everyone around her can see her, warn her, and give her room. A whole scheme with degraded receivers is a different animal because the help has been degraded along with the patient. Second compounding effect: nowhere to go. We covered this earlier, but it lands differently now. The standard response to uncertainty at sea is to buy time and space. Slow down, open out, get away from other traffic, and sort yourself out. At Hormuz, the water outside the scheme has carried advisories about mines, restricted areas, and naval activity, and regional reporting through the spring of 2026 flagged mine danger close to the lanes themselves. A deep draft vessel has an additional constraint the advisories do not need to mention. She may simply not fit outside the channel. So the safety valve that exists almost everywhere else is closed here. Third, and this is the one I did not expect and find the most interesting. The behavior that reduces your security risk in a contested strait is close to the opposite of the behavior that reduces your navigation risk. If you're worried about being attacked, you want to transit fast, minimizing the hours you spend inside the danger area. You may want to transit at night. You may want to shut off your identification broadcast so you're harder to identify and target. You may want to move in company with other ships and with a naval escort. If you're worried about a degraded navigation picture in a 2-mile lane, you want the reverse of nearly all of that. You want to slow down because speed converts a position error into a collision faster and takes away the minutes you need to sort it out. You want daylight because visual bearings and lookout work better. You want your identification broadcast running because it's how other ships understand your intentions. And you want space around you, not company. Every ship making this transit is resolving that contradiction in one direction or the other without a right answer. And that resolution is being made by a master under commercial pressure, with a charterer waiting, an insurer watching, a crew that wants to be somewhere else, and a set of advisories that describe the risk without deciding it for him. There's no procedure for that. There's judgment. And judgment is exactly the thing that runs short at 4 a.m. after several days of broken sleep. The escorted convoy is the clearest illustration. Through the crisis, several navies organized protected transits. In March of 2026, the Indian Navy escorted Indian-flagged gas carriers through the strait, under an operation it had run in the region before, the first such transit in a fortnight after commercial traffic had all but stopped. Later in the period, coverage described batches of vessels making the passage under American facilitation, around 30 ships over a couple of days at the beginning of August. Those arrangements save lives, and they are the right call. They also do something to the navigation problem. They gather ships into tight groups, moving together in a narrow lane, possibly at night, possibly with reduced broadcasting, in an area with degraded satellite navigation. Solving the security problem tightened the navigation problem. That's what a genuine dilemma looks like, and I'd rather name it than pretend the response was free. There's a fourth factor that gets almost no attention outside the profession, and it belongs here because it eats into the fallback. Radar in the Persian Gulf and its approaches behaves oddly. Very hot, dry air sitting over water that's cooler than the air above it produces layers in the lower atmosphere that bend radar energy downward, trapping it in what's called a duct. When that happens, the radar horizon can extend enormously, and echoes from far beyond the normal range appear on the screen, sometimes at ranges that make no sense because the pulse has traveled out and back over more than one sweep. In other conditions, the reverse happens and energy is bent upward, so targets that ought to be visible are weak or missing. Operators in this region know about it and are trained for it. It's a well-documented regional characteristic, and it matters here for one reason. The instrument you fall back on when satellite navigation fails is itself operating in an environment that requires interpretation. Radar remains the anchor. It's just not an anchor you can drop without thinking. Add heat haze and summer dust, which cut visual range and make visual bearings less useful, and the picture is complete. So here's the machine, whole. A 21-mile gap between two coasts, with a usable corridor 4 miles wide split into opposing lanes. Up to 150 vessels a day, some of them among the largest moving objects on Earth, needing miles to shed their way, and unable to leave the deep channel. A fifth of global petroleum consumption and a comparable share of the seaborne gas trade, with no realistic way around. A single class of navigation signal, arriving hundreds of times fainter than the receiver's own static, feeding the chart, the identification broadcast, the recorder, and the autopilot with no means of proving where it came from. A radio environment in which multiple parties operate powerful transmitters, some of them designed specifically to deny or corrupt that signal. Fallback methods that work but cost workload and expertise. In an atmosphere that complicates the main one. A safety valve, the option of opening out and slowing down that has been welded shut by mines and restricted zones. And a security situation that rewards precisely the behaviors that make the navigation harder. Nothing in that chain requires anything to break. Every element performs as designed. The failure is a property of the arrangement. That's the explanation. And if you can now walk somebody else through it, from the physics of a faint signal to a tanker apparently parked on a runway, you have it. What's left is the question of what a system does after it learns something like this about itself. The first thing that changed is the smallest and the most consequential. And it happened inside documents almost nobody outside the industry has ever read. Every ship operates under a set of standing orders from the master and a set of procedures from the company. They cover how often a fix is taken, when the master must be called, what the officer of the watch may decide alone, how the passage plan is built, what happens when an alarm sounds. They are dry, they are specific, and they are the actual operating system of a bridge. Across the fleets that trade through this region, those documents have been rewritten. The change at the center of it is a single conceptual move, and it reverses about 30 years of practice. The satellite-derived position is now to be treated as advisory. That word is doing an enormous amount of work. It makes the position an input to be corroborated, ranked alongside radar and visual bearings and depth, instead of sitting above them as the reference against which everything else gets checked. That sounds like a small semantic adjustment. It's a reorganization of the entire hierarchy of the bridge. For a generation, the satellite position was the truth, and the other methods were used to confirm it. In the new arrangement, the physical observations are the truth, and the satellite position is a claim. Everything downstream follows from which way round those sight, what alarms mean, what gets written in the log, who gets called, and above all, what a watch officer does in the moment when the display and the radar disagree. Around that central move, a set of specific practices has hardened into routine on ships transiting the region. Pre-transit briefings that explicitly cover interference, what it looks like, which methods will be used to cross-check, what the trigger is for calling the master. Passage plans annotated with the radar conspicuous objects that will be used for fixing, chosen in advance rather than hunted for under pressure. A defined fixing interval using non-satellite methods for the whole transit. Bridge manning increased for the passage, with an extra officer and additional lookouts. A helmsman on the wheel instead of track control through the confined section, both radars running on different ranges. Reporting requirements to the company and to the regional authorities when interference is experienced, so that the next ship gets the warning. Industry has put substantial guidance behind this. The main maritime associations issued a dedicated publication on jamming and spoofing, now in its second edition, aimed squarely at bridge teams. Flag states issued circulars. Protection and indemnity clubs published guidance to their members. Class societies weighed in. Trade bodies representing tanker operators, dry bulk operators, and container lines pushed material out to their fleets. The technical recommendation that recurs across almost all of it is the same. Assume the satellite position may be wrong, verify it against something physical, and know in advance what you'll do when it is. There's a word that keeps appearing in the newer material, and I think it's the right one: sensor management. The idea is that the modern watch officer's core competence has become the adjudication between instruments, which is a very different skill from operating them. Knowing which sensor is reliable under which conditions, which ones share a common input and will therefore fail together, and which ones are independent in fact. That's a different job description than the one most of the current fleet's officers trained for, and it's a more demanding one. Now, the part of this I think deserves more attention than it gets. All of that lands on people. Specifically, it lands on a bridge team of a handful of officers, on a ship whose manning levels were set on the assumption that automation had reduced the workload, in a job where fatigue is already a recognized and chronic safety problem. Consider what the transit now involves for the officer of the watch: continuous manual fixing, continuous interpretation of a radar picture in an atmosphere prone to anomalous propagation, continuous evaluation of an identification display in which some contacts are truthful, some are corrupted, and some are absent. Traffic dense enough that collision avoidance is a full task by itself. Radio traffic on multiple channels. The master on the bridge, which helps, but also adds the pressure of being watched. And underneath it all, the knowledge, unavoidable and unhelpful, that this is a strait where merchant seafarers have been killed in the past year. Seafarers on international ships work contracts that commonly run 6 to 9 months, sometimes longer, with limited shore leave, in a workplace they cannot leave. When the International Maritime Organization reported in April of 2026 that roughly 20,000 mariners were caught inside the Gulf on around 2,000 ships, that was a welfare situation as much as a logistics one. Contracts expiring with no way to get crew off, relief crews unable to get on, people sitting at anchor in temperatures that make the accommodation block a difficult place to sleep, watching the news. Nothing about the technology story matters more than that, and it's the part most likely to be left out, because the instruments are photogenic and the crew rosters are not. There's a second-order effect worth naming too. Skills that were allowed to atrophy do not come back on demand. If you qualified as a deck officer in the past 25 years, you were trained on radar, and you were trained to fix by radar, and the certification requires it. But the amount of practice you got in doing it for real, hour after hour, in heavy traffic, under time pressure, without a satellite position on the screen as a safety net, depends entirely on the ships you sailed on and the masters you sailed under. Some companies never let the habit go and drilled it. Others did not. The industry is discovering, in real time and in the least forgiving location available, which of its officers are which. None of that is the fault of the officers. It's the product of a training and operational culture that quietly allowed a core competence to become a certification box, because for 25 years, the underlying capability was never actually needed. The people paying for that now are the ones standing the watch, and the effects are not confined to the strait. Interference does not respect the boundary of the region that produced it. A ship that transits Hormuz carries the experience of it to her next port, and her next crew, and her next company. A generation of officers is being trained by circumstance in a skill set that the previous generation was allowed to let go of. If there's a silver lining in any of this, that's where I'd look for it. The fleet is relearning something it should never have stopped knowing, and it's relearning it the hard way, which is the way that sticks. Meanwhile, the same set of facts was working its way through a completely different system, one that has no bridge, no radar, and no crew, and that responds to risk with a single instrument: price. Marine insurance is one of the oldest continuously operating risk markets in the world, and it has a habit that makes it useful as an instrument. It prices things it does not fully understand, quickly, in public, and then adjusts. A merchant ship carries several distinct layers of cover. Hull and machinery insures the vessel herself. Protection and indemnity, provided through mutual clubs owned by ship owners, covers third-party liabilities. Pollution, wreck removal, cargo claims, injury to crew. And war risks cover sits separately, because ordinary policies exclude war, and it works differently. It's bought voyage by voyage into designated areas, at an additional premium quoted as a percentage of the value of the hull, and it gets repriced the moment the market's view of a region shifts. The designation of those areas is handled, for a large part of the market, by a body at Lloyd's called the Joint War Committee, which maintains a list of regions where vessels are considered exposed to war-related perils. Getting listed does not forbid a voyage. It changes what the voyage costs, and it obliges an owner to notify underwriters before entering. The Gulf has been on and off that list for decades. In 2026, it went firmly on, with the committee redesignating the whole of the Arabian Gulf as a conflict area. The numbers that followed are worth walking through slowly, because they measure something that would otherwise be invisible. Before late February of 2026, the additional premium for a transit of the Strait of Hormuz was, according to market reporting from the period, somewhere in the region of 0.25% of the hull's value, with some accounts putting the earlier baseline lower still, closer to 0.1% before tensions began climbing. On a large tanker worth in the neighborhood of $100 million, that's a cost measured in the low hundreds of thousands per transit, real money, and thoroughly manageable inside the economics of a cargo worth far more. Within 48 hours of the strikes that opened the crisis on the 28th of February, reporting described war risk premiums rising roughly fivefold. Underwriters canceled existing cover and reoffered it at multiples of the old rate. At the peak, quotes reported in the market reached as high as 10% of a vessel's value for a single passage, and through the following months, industry estimates put the working range at somewhere between 3 and 8%. On that same hypothetical $100 million tanker, that's an insurance bill in the millions of dollars to make one transit of one strait. Then something happened that matters more than the price. In early March, parts of the market withdrew. Reporting described protection and indemnity cover being removed for transits, and several major insurers pulling back entirely. That's a different event from an expensive premium. A ship without third-party liability cover cannot realistically trade. Ports will not accept her. Charterers will not fix her. And the owner is personally exposed to a pollution liability that could run into the billions. The phrase that circulated in the coverage at the time was that the strait had become legally open and economically closed, which captures it exactly. The right of transit passage under the law of the sea was completely intact. There was simply no commercially rational way to exercise it. Governments moved in behind the market, which is what governments do when a private risk becomes a public one. Reporting in March described the United States extending support to insurers through its terrorism risk insurance framework. Analysis published by the World Economic Forum during the crisis described the broader pattern. States stepping into the role of insurer of last resort when commercial underwriting for a strategic corridor collapses. That's an old mechanism, used for aviation after the attacks of 2001 and for shipping in previous Gulf conflicts, and its reappearance is one of the clearest signals available that a situation has moved from expensive to structural. The knock-on effects ran outward from there. Freight rates for tankers on routes out of the Gulf rose sharply, because a ship taking that risk has to be paid for taking it. Charterers rerouted where they could and paid where they could not. Crude prices reflected it. Reporting had Brent crude passing $100 a barrel in early March for the first time in 4 years, with a peak in the region of $126 during the worst of it. Now, none of that is caused by satellite navigation interference specifically. Let me be precise, because this is exactly the kind of causal chain that gets sloppy. Those premium movements are driven overwhelmingly by the physical risk to ships from attack, which is a different hazard and a far more direct one. Interference is one strand inside a much larger risk picture. And it would be dishonest to hand it credit for the whole move. What interference has done is more specific and over the long run, probably more durable. It's changed what underwriters ask about. Marine underwriting has always been partly about the ship and partly about the operator. An underwriter looks at the age of the hull, the class society, the flag, the owner's casualty record, the crewing arrangement, the trading pattern. The newer questions concern navigational resilience. What receivers are fitted, whether the ship can use more than one satellite constellation, whether there's an inertial system aboard, what the company's procedures say about interference, whether the crew has been trained and drilled on it, whether the ship reports interference when it experiences it. Guidance published by war risk insurers and by the protection and indemnity clubs through this period spells out the expectations plainly enough that an owner who ignores them is taking a documented position. That's the mechanism by which insurance changes behavior. It rarely forbids anything. It simply makes the resilient option cheaper than the fragile one, over enough voyages. And then the fleet moves. There's an unresolved legal question sitting underneath all of this, and marine lawyers have been circling it since the interference became widespread. It goes like this. Under the international rules governing carriage of goods by sea, a carrier owes a duty to exercise due diligence to make the ship seaworthy before and at the beginning of the voyage. And seaworthiness includes being properly manned, equipped, and supplied. There's also a long-standing defense available to carriers for loss arising from errors in the navigation or management of the ship. So suppose a vessel is spoofed and grounds, and the cargo is lost. Is the owner protected by the navigational error defense on the grounds that the crew made a decision on the basis of information they had no reason to doubt? Or is the ship unseaworthy on the grounds that in 2026, sailing into a strait with well-publicized interference, carrying a receiver with no ability to detect it, and a crew with no procedure for it, falls short of due diligence? Nobody knows. That question will be answered by courts and arbitrators, case by case, over years. And the answers will depend on facts that have not yet been litigated. What I'd say with confidence is that the existence of the question has already changed behavior, because owners and their lawyers can read the direction of travel. When the published guidance is this explicit and this widely circulated, the argument that nobody could have known gets weaker every month, which points at the deeper problem, the one that the money cannot solve and the courts cannot reach. Radio spectrum is governed internationally, and it's governed rather well, which is why your phone works in a foreign country and why an aircraft's altimeter does not get swamped by a television transmitter. The instrument is the International Telecommunication Union's radio regulations, a treaty-level document that allocates bands, sets technical limits, and binds essentially every state on Earth. Within that framework, certain services get elevated status. Radio navigation is designated a safety service, and the regulations state plainly that all stations are forbidden from causing harmful interference to radio navigation and other safety services. That's about as clear a prohibition as international radio law contains, and the reason is obvious. Interference with a broadcast station wastes an evening. Interference with a navigation service kills people. So on the face of it, this is already illegal. What's happening in the Gulf and in the Baltic and in the Black Sea is a treaty violation many times over. Now find the enforcement mechanism. The Union operates by cooperation. A state that suffers harmful interference reports it. The Union facilitates investigation, and the state responsible is expected to identify and stop the source. That machinery works remarkably well for the ordinary case, which is an accident, a badly filtered transmitter, a misconfigured installation, an unlicensed operator. It works because the state hosting the source generally wants the problem fixed and has nothing at stake in continuing. It has no answer at all for a state that's doing it on purpose, in wartime, from its own territory, for reasons it considers existential. And there's a provision that makes the gap wider. The regulations acknowledge that states retain freedom in the operation of military radio installations. The obligation attaching to those installations is softer. They must, so far as possible, observe the measures taken to prevent harmful interference. So far as possible is doing an enormous amount of work in that sentence, and every state operating electronic warfare equipment in a conflict knows it. The law of the sea has a parallel hole, and we brushed against it early on. Transit passage through an international strait cannot be suspended or impeded. That's a strong protection, and it has held up. Even at the worst points of this crisis, the legal position that the strait must remain open to transit has been asserted by many states and disputed by few in principle. But a rite of passage is a right to be somewhere. Nothing in the convention obliges any state to allow you to know where you are while you exercise it. The drafters were working in the 1970s, finalizing in 1982, in a world where a ship's position came from her own observations of the sky and the sea, and from shore stations she could choose to use or ignore. The idea that navigation might depend on a fragile signal from orbit that a third party could switch off was not a scenario anyone needed to legislate for. So the international framework guarantees your right to pass, forbids interference in principle, and provides no mechanism to stop it in the one situation where it actually happens. What the institutions can do, they have been doing. The International Maritime Organization has pushed this steadily up its agenda as the reports accumulated, with its safety committee circulating guidance urging member states to take the actions necessary to minimize interference emanating from their territory, which is a polite way of pointing at the radio regulations and reminding everyone they signed. It has issued joint statements with the Civil Aviation Organization and the Telecommunications Union calling for satellite navigation to be protected. Its Subcommittee on Navigation and Communications has taken up resilient positioning as a work item. Through 2026, there has been sustained pressure from within the organization for states to treat this as a safety of life issue, and not merely as an operational nuisance. There's also a quieter regulatory move that I think will end up mattering more than the statements, because it changes an obligation rather than expressing a hope. Under the Safety Convention, a master is required to report dangers to navigation. That's an old duty, and it covers the things you'd expect: ice, derelicts, uncharted hazards, aids to navigation out of position, severe storms. The list was written for physical objects. Several authorities and industry bodies now treat significant satellite navigation interference as a reportable danger to navigation and encourage or expect masters to file it through the established channels. That's a small change with a large effect because it converts a private inconvenience into a logged, aggregated, publishable data point. And aggregation is what turned this from a set of complaints into a measured phenomenon with maps and counts attached. That's roughly where the law stands. The rite of passage is intact. The prohibition on interference is clear and unenforceable against a determined state. The reporting obligation has been quietly widened, and the practical response has been pushed down onto the operators, which is to say onto the ships, which is to say onto the crews, which is why the most serious work happening on this problem is engineering work, and it's aimed at a single question: how do you build a receiver that can tell the truth from a good imitation? The answers fall into three families, and it's worth understanding what each can and cannot do, because they're routinely lumped together in a way that obscures a critical asymmetry. The first family is about listening more widely. When satellite navigation began, there was one constellation. Now there are 4 global ones, operated by the United States, Russia, the European Union, and China, plus regional systems, broadcasting across several frequency bands. A receiver that can use all of them at once is significantly harder to defeat, because an attacker has to cover every band and every constellation simultaneously to fully deny it, and a spoofer has to generate a coherent counterfeit of all of them at once to fully deceive it. A multi-constellation, multi-frequency receiver does not make you immune. It raises the cost of the attack, sometimes by a lot, and where the interference is somebody's spillover from a job aimed at something else, raising the cost is often enough. The second family is about listening more cleverly, in a directional sense. Remember the fingerprint from earlier. Real satellite signals arrive from scattered points across the sky, while a simple spoof arrives from one antenna on one bearing. An antenna array with several elements can measure the direction a signal is coming from and can be steered electronically to reject energy from a particular direction. That's what a controlled reception pattern antenna does, and it's been standard in military applications for years. Point it at the sky, null out the horizon, and a transmitter on a headland becomes very much quieter while the satellites stay audible. It's effective and it's expensive, and the equipment has historically been sized and priced for aircraft and warships, and not for the monkey island of a bulk carrier. And the third family attacks the root of the problem, which is that the civilian signal has never carried any proof of who sent it. Authentication is the elegant answer, and it took a long time to arrive. The original civilian signal was designed in an era when nobody imagined an adversary bothering to counterfeit it, and it carries no proof of origin whatsoever. Any transmitter that produces the correct code structure is, from the receiver's perspective, a satellite. There's no seal to check. Europe's Galileo system closed that gap. Its Open Service Navigation Message Authentication, which everybody calls by its acronym, attaches cryptographic signatures to the navigation message the satellites broadcast. A receiver holding the public keys can verify that the message it just received originated with Galileo and has not been fabricated or altered. The service reached full operational status in July of 2025, making Galileo the first global constellation to offer signal authentication as part of its ordinary civilian service, free to anyone with a receiver that can use it. Work toward comparable capability on the American system has been under development for years. That's a real defense against spoofing, and it's the right shape of defense because it addresses the actual defect instead of managing the symptoms. But here's the asymmetry I flagged, and it's the single most important thing to understand about where this ends up. Authentication does absolutely nothing against jamming. A cryptographic signature proves that a message you received is genuine. It has no opinion about a message you never received. If somebody floods the band with noise until the correlation can no longer dig the signal out of it, an authenticated signal you cannot hear is just as absent as an unauthenticated one. The two attacks are different in kind, and they need different countermeasures. And any account that treats one solution as fixing both is selling something. So the counter to jamming has to come from somewhere other than the satellites. And there are three serious candidates. The oldest is terrestrial radio, and specifically an updated form of the long-range navigation systems that were switched off in the 2000s. Enhanced LoRaN transmits at low frequency and very high power from ground stations, which reverses every disadvantage the satellite signal has. It arrives strong. It penetrates. It's difficult to jam without a transmitter of comparable power, which is difficult to hide. Its geometry is poor compared with satellites, so the position it gives is coarser, but coarser and reliable in a 2-mile lane is worth a great deal. South Korea has built and demonstrated a working system as a resilience layer, and there has been an on and off argument in Britain, the United States, and parts of Europe about whether to rebuild what was dismantled. The maritime case for it has been argued forcefully by mariners and by underwriters, and the counter-argument has always been cost, since somebody has to pay to run transmitters that are, Ukraine, in the normal case, doing nothing. The second candidate is cleverer and cheaper. Use the radio infrastructure that already exists along every coast. Ranging mode, usually written as R mode, takes the signals that maritime radio beacons and coastal identification base stations are already transmitting and modifies them slightly so that a receiver can measure the range to each one. The infrastructure is already installed, already maintained, and already positioned exactly where ships need it, which is near the coast, in confined waters, where a position error hurts. The International Association responsible for marine aids to navigation has been working this problem for years, and trials have run in several regions. The third is the one that requires nothing from anybody: inertial navigation. A set of accelerometers and gyroscopes measures every acceleration and rotation the ship experiences and integrates them forward from a known starting point. It listens to nothing. There's no signal to jam, no message to counterfeit, no antenna to point. Its weakness is drift, since small errors accumulate over time. But the drift over the hours of a straight transit is bounded and modest, and it degrades gracefully in a way that a satellite receiver under attack does not. Inertial systems used to be enormous and cost a fortune. Fiber optic gyroscopes and precision micro-machined sensors have brought them into a price range where fitting one to a merchant ship is a commercial decision instead of a fantasy. And then there's the research frontier, which is the fun part. Zach Cassis, an electrical engineer at Ohio State University, has spent years developing navigation from what the field calls signals of opportunity, radio transmissions that were never intended for positioning at all. Cellular network signals, the broadband constellations in low Earth orbit that have proliferated over the past decade, which are much closer than navigation satellites and therefore arrive far stronger. His group has reported sub-meter accuracy for unmanned aircraft using cellular signals, close to lane-level accuracy on the ground, and meter-level results using low-orbit satellites. His framing for why this matters is the phrase I keep coming back to: security by diversification. The vulnerability at the bottom of all this is a monoculture problem: one signal, one architecture, one point of attack. The fix is more kinds of signal, arriving from more directions, produced by systems that fail for unrelated reasons. That's the technology. Now the uncomfortable part, which is arithmetic rather than engineering. A merchant ship has a working life of 20 to 30 years. Bridge equipment gets replaced at survey intervals, at major refits, or when it breaks. There are somewhere over 100,000 merchant vessels in the world fleet. Nobody sits down and decides to fit all of them with authenticating multi-constellation array antenna receivers backed by inertial systems. What happens is a 2-decade replacement cycle driven by economics, regulation, and the ordinary attrition of equipment, and the recent observation that the typical shipboard satellite receiver runs about 15 years behind the state-of-the-art tells you where in that cycle the fleet currently sits, which is why the practical answer, for the next decade at least, is the one sitting on the bridge already: people. The training has moved. Maritime academies and commercial training centers run satellite-denied scenarios in full mission simulators where a bridge team discovers mid-transit that the position has gone bad and has to work the ship through on radar and eyes. Courses in celestial navigation, which spent a couple of decades looking like a heritage skill, have found their students again. The United States Naval Academy, which had dropped celestial from the core curriculum, brought it back in the middle of the last decade, and the reasoning given at the time was explicitly about resilience when satellite systems cannot be relied on. Merchant training institutes still teach it at operational level and are still filling the seats. It would be easy to romanticize this, and I would rather not, because a sextant is no answer to a 2-mile lane at night in heavy traffic. Celestial navigation needs a visible horizon and visible bodies, gives you a fix good to a mile or so at best, and takes time you may not have. Its value in this context is narrower and more interesting than the romance suggests. It's proof that a competent mariner can establish position from the physical world using nothing that anyone can transmit at, and the confidence that comes with knowing you could. The working tools in the Strait are radar, the sounder, the gyro, and the eye. The sextant is the reminder of what those tools belong to. So here's where it has landed. In the summer of 2026, ships still transit, fewer of them, slower, in groups, often escorted, sometimes silent, at a cost in insurance that would have been unthinkable 2 years ago. Traffic through the strait in the first quarter of the year ran nearly 30% below the year before. Interference continues to be reported almost daily, and advisory notes continue to log disruption events in the hundreds. The rite of passage has never been legally in doubt for a moment, and the thing that changed permanently is smaller than any of that, and harder to reverse. For about 30 years, a mariner could look at a number on a screen and know where the ship was. Not estimate, No. That was a new condition in the history of seafaring. It lasted a little over a generation, and in one specific stretch of water, it has ended. The number is still there. It's just become a claim now, and claims get checked. One thing I would like from you, and it's specific. Somebody listening to this has stood a watch. Somebody has flown an approach where the box started arguing with the world outside the windscreen. Somebody has run a survey, or a drilling rig, or a combine on satellite guidance, or has simply been driving at night when the phone insisted, with total confidence, that the road under the car did not exist. That moment, where the instrument says something impossible, and you have to decide whether to believe it. Is this entire subject in miniature? So put yours in the comments. What did the instrument tell you? What made you doubt it? And what did you go and check first? The ones from people who do this for a living tend to be worth reading twice. And if this is the kind of thing you want more of, the like and the subscribe are how you say so. One last picture. Somewhere off the Musandam Peninsula tonight, a third mate is standing at a radar, taking a range off a limestone cliff that has been in exactly the same place since long before there were ships to measure it. He's writing the fix on a chart in pencil. 2 feet away, a screen is showing him a position that may or may not be real, and he has decided for the next few hours that the cliff outranks the screen. Everything astern of him in that lane depends on him being right about which of the two to trust. That is what the modern bridge has quietly turned into, a place where the newest instrument aboard gets marked against the oldest thing in sight.